The Middle America Trench marks a massive tectonic boundary. Here, the dense oceanic Cocos Plate grinds beneath the lighter continental Caribbean Plate at a steady rate of 7 to 8 centimeters per year. This subduction generates two earthquake types. First, offshore, within the sinking Cocos Slab. At 60 to 80 kilometers, plate bending creates extensional forces, triggering normal slip earthquakes. Second, inland, beneath the volcanic arc. At depths under 20 kilometers, the continental crust experiences strike-slip motion, grinding horizontally. El Salvador's seismic profile is defined by these two distinct mechanical regimes, operating at different depths and with different fault kinematics. On June 19, 1982, a magnitude 7.3 offshore earthquake ruptured deep inside the sinking Cocos Slab. On October 10, 1986, a magnitude 5.7 shallow strike-slip earthquake struck inland directly beneath the capital city of San Salvador on the volcanic arc. A 4-year gap separated these two events, which originated in different tectonic environments. In January 2001, the pattern repeated on a larger scale. A massive magnitude 7.7 intra-slab earthquake tore through the offshore subduction zone. 1 month later, on February 13th, a magnitude 6.6 upper crustal earthquake shattered the inland volcanic arc. If these deep offshore faults and the shallow inland faults were independent, this recurring sequence would be a statistical outlier. The proximity of these events suggests they are not independent clusters. The offshore activity appears to be the mechanical driver for the subsequent crustal ruptures. To find the link between the ocean floor and the continent, we have to look at the structural receiver in the overriding plate, the El Salvador fault zone. This fault zone is a continuous right lateral strike-slip system extending over 100 kilometers. It is oriented 90 to 100 degrees east, accommodating trench parallel motion along the volcanic arc. This radar map shows the trace of the El Salvador fault zone. At the markers for the Rio Lempa and Rio Grande de San Miguel, you can see sharp geographic deflections. The river networks have been dragged horizontally by continuous strike-slip movement. The El Salvador fault zone is perfectly oriented and mechanically primed to absorb sudden stress changes from the surrounding region. Geologists measure these stress changes using the change in Coulomb Failure Stress. The equation determines whether a fault is closer to sliding. The first variable is change in shear stress, pushing parallel to the fault plane. The second is change in normal stress, clamping the fault shut. If unclamped, friction drops, making sliding easier. These forces are multiplied by the apparent friction coefficient, which accounts for the material properties of the fault. In these regional models, the coefficient is set at a standard baseline of 0.4. Ruptures are not just isolated releases of energy. They act as mechanical triggers that redistribute stress across the regional fault network. We apply this mathematics to the 1982 to 1986 events by modeling the June 1982 offshore rupture as an extensional, normal slip event. This map shows the static stress transfer projected onto a horizontal receiver plane at a 10-kilometer depth, mimicking the fault zone. The 1982 rupture projected a distinct lobe of positive Coulomb stress change, the red and yellow zone, directly inland, crossing the black fault line. The positive values between 0.1 and 0.3 megapascals promote faulting, while the negative blue values inhibit seismic activity by clamping faults shut. The white star on this map marks the epicenter of the shallow 1986 earthquake that occurred 4 years later. It sits within the positive stress lobe. The initiation point for the 1986 rupture aligns with the stress increase generated by the 1982 offshore quake. The 1986 crustal rupture occurred exactly where offshore geodynamics dictated. The deep subduction event loaded that specific fault segment, pushing it past its failure threshold. This same mathematical model explains the sequence of 2001. On January 13th, the massive magnitude 7.7 offshore subduction event occurred. Panel B models stress transfer from this larger subduction event. The positive stress zones are far more expansive, heavily loading the middle segment of the El Salvador fault zone. The black dots representing aftershocks of the February 2001 inland earthquake are contained entirely within it. The February upper crustal rupture zone matches the area that experienced a stress increase of over 0.1 megapascals just 1 month prior. The 2001 sequence was a mechanical cascade, governed by static stress loading from the subducting plate to the overriding crust. The question remains whether all deep subduction earthquakes trigger shallow inland faults. The data provides a negative constraint. When geologists model reverse slip earthquakes, where compressive forces push rock upward, the results change. At the same distance from the coast, reverse slip kinematics generate stress decreases on the El Salvador fault zone. They clamp the inland faults shut, creating a stress shadow. This specificity proves that the loading process depends on the orientation of the initial subduction event. Only extensional, normal slip events load the volcanic arc. Panel E combines the 1982 and 2001 events into a joint model. White dashed arrows connect offshore subduction events to the inland crustal ruptures they triggered. Now, notice the critical anomaly on the eastern side of the fault zone, marked by a question mark. The February 2001 event loaded this specific, unruptured eastern segment of the fault with a positive stress change exceeding 0.15 megapascals. A future offshore extensional event located to the southeast would reload this area, driving it closer to failure. In El Salvador, regional fault systems cannot be assessed as independent variables. The location of the next deep subduction event dictates where the next shallow crustal disaster will strike.